Welcome to Sleepy Astronomy. I'm truly happy you've arrived. Let your breath slow and the day settle behind you as your mind drifts gently into the quiet of space. Tonight, we're turning our gaze far beyond the Milky Way, toward a distant shimmer that rests softly in the dark. There exists in the night sky a patch of light so faint that you might miss it if you do not know where to look. Yet, this subtle glow represents something extraordinary. It is the Andromeda Galaxy, our nearest large galactic neighbour, floating in the darkness 2.5 million light years from Earth. On autumn evenings in the northern hemisphere, when the air grows crisp and clear, you can find it with your naked eyes if you venture far enough from city lights. Look toward the constellation Andromeda, named for the princess of Greek mythology, and there it appears, a smudge, a blur, a ghostly wisp against the black. The light entering your eyes at this moment began its journey across the cosmos when our ancestors were just learning to fashion stone tools. Later, when that light departed Andromeda, the beings we would become had only recently begun to walk upright on the African savanna. They had no language as we understand it, no written word, no concept of stars as distant suns or galaxies as island universes. Yet, the photons traveled faithfully across the expanding void, crossing incomprehensible distances to arrive at this precise moment, to strike the retina of a creature capable of understanding what they represent. Ancient astronomers has noticed this peculiar smudge long before anyone understood its true nature. The Persian astronomer Abd al-Rahman al-Sufi recorded it in the year 1964, describing it in his book of fixed stars as small cloud. He observed from the clear, dark skies of Persia, where the Milky Way stretched overhead like a river of light, and the heavens revealed their secrets to patient watchers. Al-Sufi could not have known he was documenting an entire galaxy, a vast collection of hundreds of billions of stars. To him, it was simply a curiosity, a nebulous object that did not fit neatly into the categories of stars and planets that dominated astronomical thinking. For nearly 1,000 years after Al-Sufi's observation, Andromeda remained a mystery. It appeared in star catalogues as the Great Nebula in Andromeda, a designation that revealed nothing about its fundamental nature. European astronomers, with their increasingly sophisticated telescopes, could see that it possessed structure, that it was not merely a formless cloud, but something organized, something with shape. They observed a bright central core surrounded by a diffuse glow. Some thought it might be a solar system in the process of formation, a disk of material gradually condensing into planets around a nascent star. Others speculated it was a nebula of glowing gas, similar to the clouds they observed elsewhere in the Milky Way. The invention of photography transformed astronomy in ways that are difficult to overstate. Photographic plates could accumulate light over long exposures, revealing details invisible to the human eye, no matter how long an astronomer stared through an eyepiece. When astronomers turned their cameras toward Andromeda, they discovered spiral structure. The galaxy revealed arms winding outward from its bright center, lanes of darkness between them, a shape that suggested rotation and organization on a massive scale. Yet still, the fundamental question remained unanswered. Was this object part of our own stellar system, or was it something else entirely? Was it nearby or incomprehensibly distant? The answer to this question would determine whether the universe we inhabited was small and comprehensible, or vast beyond all previous imagination. The debate that would resolve this question reached its climax on April 26, 1920. Two prominent astronomers, Harlow Shapley and Heber Curtis, presented opposing views in what became known as the Great Debate. Shapley argued that spiral nebulae, including Andromeda, were relatively nearby objects within our own Milky Way galaxy. He believed the Milky Way itself was enormous, perhaps 300,000 light-years across, and that it represented the entirety of the universe. Curtis took the opposite position. He suggested the spiral nebulae were island universes, separate galaxies like our own, scattered throughout a much larger cosmos. The evidence on both sides was fragmentary and inconclusive. The astronomical community remained divided. The resolution came not from theoretical arguments, but from careful observation and measurement. Edwin Hubble, working with the 100-inch Hooker telescope at Mount Wilson Observatory in California, began a systematic study of Andromeda in 1923. He was searching for a particular type of star called a Cepheid variable. These remarkable objects pulse with regular periods, brightening and dimming in a predictable rhythm. Earlier work by Henrietta Swan Leavitt had established a crucial relationship. The period of a Cephid's pulsation relates directly to its intrinsic brightness. Measure the period, and you know how bright the star truly is. Compare that intrinsic brightness to how bright it appears from Earth, and you can calculate its distance. It is a cosmic yardstick, a way to measure distances across the universe with unprecedented accuracy. On the night of October 5th, 1923, Hubble found what he was searching for. He identified a Cepheid variable star in Andromeda. Over the following months, he found more. He measured their periods carefully, applied Leavitt's relationship, and calculated the distance to Andromeda. The result was staggering. Andromeda lay approximately 900,000 light-years away, a figure later revised upward to over 2 million light-years as our calibrations improved. This single measurement transformed our understanding of the universe overnight. Andromeda was not a nebula within our galaxy. It was a separate galaxy entirely, a vast collection of stars comparable to our own Milky Way, floating in the depths of space at distances that defied comprehension. The universe was not millions of light-years across, it was billions, and it contained not one galaxy, but multitudes beyond counting. The implications rippled through science and philosophy. Humanity occupied not just one planet among many in our solar system, not just one solar system among billions in our galaxy, but one galaxy among countless others scattered throughout an almost infinite cosmos. Our significance, already diminished by Copernicus and Galileo and Darwin, shrank further still. Yet paradoxically, our understanding expanded. We were small, yes, but we were capable of comprehending our smallness. We could reach across millions of light-years with our instruments and our mathematics, and bring distant galaxies within the grasp of human knowledge. Andromeda stretches across approximately 220,000 light-years of space, making it substantially larger than our own Milky Way. To put this in perspective, light itself, traveling at 300,000 kilometers per second, requires 220,000 years to cross from one edge of the galaxy to the other. The distances involved are so vast that our terrestrial units of measurement become absurd. If you could somehow travel at the speed of a commercial airliner, it would take over 200 billion years to traverse Andromeda's diameter. The universe itself is only 13.8 billion years old. You could make the journey 15 times over in the age of everything that exists. The galaxy structure follows a pattern common among spiral galaxies. At its heart lies a dense central bulge, a roughly spherical concentration of stars that glows with the combined light of billions of ancient suns. These stars are old, their surfaces cool and red. They orbit the galactic center in random orientations, a disordered swarm held together by mutual gravitational attraction. Surrounding this bulge, a flattened disk extends outward, traced by graceful spiral arms that wind through the galaxy like cream stirred into coffee. These arms are not solid structures, but density waves, regions where stars and gas temporarily concentrate as they orbit. They mark the sites of star formation, where vast clouds of hydrogen collapse under their own gravity to ignite as new stars. The disk itself is remarkably thin compared to its diameter. If you were to scale Andromeda down to the size of a compact disk, it would be proportionally thinner than that disk. Yet, within this relatively narrow plane, hundreds of billions of stars pursue their orbits around the galactic center. They move at hundreds of kilometers per second, velocities that would seem tremendous by terrestrial standards, but translate to stately, almost imperceptible motion when viewed from our distant vantage point. A star on the outskirts of Andromeda's disk takes hundreds of millions of years to complete a single orbit. In all the time humans have existed as a species, that star would not have moved appreciably in its circuit around the galaxy. Extending far beyond the visible disk, Andromeda possesses a spherical halo of ancient stars and globular clusters. These objects follow highly elliptical orbits, plunging through the disk and soaring to great heights above and below it before falling back again. They represent the oldest components of the galaxy, formed over 10 billion years ago, when the universe was young and galaxies were still assembling from smaller fragments. The halo is not uniform or symmetric. It contains streams and shells of stars, the remnants of smaller galaxies that Andromeda has consumed throughout its history. These fossil structures preserve evidence of ancient collisions and mergers, cosmic violence that unfolded over billions of years. At the very center of Andromeda, in the densest region of the bulge, lies a supermassive black hole. This object contains approximately 140 million times the mass of our Sun, compressed into a region smaller than our solar system. It is not the largest supermassive black hole known to astronomy, but it is substantial nonetheless. The black hole exerts a powerful gravitational influence on the surrounding stars, which orbit at tremendous velocities in its vicinity. By measuring these stellar velocities, astronomers can calculate the black hole's mass with remarkable precision. The stars themselves remain invisible at our distance, but their cumulative light and their effect on the galaxy's structure reveal the monster lurking in the depths. Curiously, observations of Andromeda's nucleus reveal what appears to be a double structure, two concentrations of light separated by small distance. For years, astronomers debated whether this indicated two supermassive black holes orbiting each other, perhaps the remnant of a past galactic merger. More recent observations suggest a different explanation. The galaxy's disk may be slightly warped or tilted as it passes through the nucleus, creating the appearance of a double peak when viewed from our particular angle. The black hole itself remains singular, anchored at the galaxy's exact center, the gravitational anchor point around which everything else revolves. The galaxy rotates, but not as a solid body. Stars closer to the center complete their orbits more quickly than those farther out, creating differential rotation that winds the spiral arms tighter over time. Yet paradoxically, the arms persist. They do not wind up completely and disappear. This is because the arms are not composed of the same stars over time. They are waves of density that propagate through the disk, regions where stars and gas temporarily bunch together. Individual stars drift in and out of the arms as they orbit, spending some fraction of their journey enhanced by the arm's density and the rest in the relatively empty spaces between. The spiral pattern itself rotates at a different speed than the stars, maintaining its structure over hundreds of millions of years through this elegant mechanism. Within Andromeda's spiral arms, vast molecular clouds collapse to form new stars. These stellar nurseries contain enough raw material to create millions of solar masses of new stars. The process begins when a cloud becomes unstable, perhaps triggered by the shockwave from a nearby supernova or by the compression of the spiral density wave. Gravity overcomes the gas pressure, and the cloud begins to collapse. As it contracts, it fragments into smaller clumps, each of which continues to collapse independently. The centers of these clumps grow hot and dense until nuclear fusion ignites, converting hydrogen into helium and releasing the energy that makes stars shine. The most massive stars burn brilliantly but briefly, exhausting their nuclear fuel in mere millions of years. The least massive smolder for trillions, far longer than the current age of the universe. The light we receive from Andromeda contains within it the story of the galaxy's history, written in the language of starlight and encoded in spectra. When astronomers separate this light into its component wavelengths, they can identify the chemical elements present in the stars and gas. They can measure velocities through the Doppler shift, the stretching or compression of light waves from objects moving away or toward us. They can determine temperatures from the distribution of wavelengths, ages from the colors of stellar populations. The ancient stars in the halo burn red and cool, their surfaces enriched with relatively few heavy elements, because they formed before many generations of stellar nucleosynthesis had occurred. The young stars in the disk shine blue and hot, their spectra revealing higher concentrations of carbon, nitrogen, oxygen, and heavier elements created in previous generations of stars. The evidence written in this starlight tells a story of violence and consumption. Andromeda has not grown to its present size through the gradual accumulation of gas from intergalactic space alone. It has devoured smaller galaxies throughout cosmic history, absorbing their stars and gas and dark matter into its own structure. The proof of this cannibalism appears in the streams of stars that loop through Andromeda's halo. These streams are tidal debris, stars torn from smaller galaxies by Andromeda's gravitational field as they passed too close. The streams maintain coherent structures for billions of years, allowing astronomers to trace them back to their origins and reconstruct the history of Andromeda's growth. Some of these merger events occurred recently in cosmic terms, within the last few billion years. Others happened long ago, in the early universe when galaxies were still young and mergers were more common. Each collision added mass to Andromeda and stirred its structure, triggering bursts of star formation as gas clouds collided and compressed. The disk itself may have formed from the merger of two smaller disk galaxies early in cosmic history, their individual structures combining to create the more massive disk we observe today. The exact sequence of events remains uncertain, but the general picture is clear. Andromeda grew through accretion and merger, consuming its smaller neighbors and incorporating them into an ever larger whole. Two substantial satellite galaxies orbit Andromeda today, having somehow escaped consumption. Messier 32, a small elliptical galaxy, contains several billion stars in a compact, spheroidal configuration. Messier 110, larger and more diffuse, possesses approximately 15 billion stars in its own elliptical structure. Both orbit Andromeda like moons around a planet, though the scales are obviously far larger. They will likely merge with Andromeda eventually, perhaps in a few billion years, adding their mass to the parent galaxy. Their present existence offers astronomers an opportunity to study satellite systems around spiral galaxies, systems analogous to the Magellanic Clouds that orbit our own Milky Way. Beyond these two prominent satellites, Andromeda possesses numerous smaller companions. Dwarf galaxies containing millions or tens of millions of stars circle the giant galaxy, most too faint to see without powerful telescopes. Some consist primarily of old stars, their star formation having ceased billions of years ago. Others contain gas and continue forming new stars, though at modest rates. These dwarf galaxies are important for understanding galaxy formation and dark matter. Their internal motions reveal the presence of dark matter halos, far more massive than their visible components. They serve as laboratories for studying dark matter in relatively simple systems, less complicated than the giant galaxies they orbit. The question of how many satellite galaxies Andromeda possesses remains incompletely answered. Astronomers continue discovering new dwarf galaxies in Andromeda's vicinity, some so faint they contain fewer than 1 million stars total. The faintest galaxies approach the limit of what our telescopes can detect at Andromeda's distance. Each new discovery refines our understanding of the galaxy's satellite system and provides data for testing theories of galaxy formation. The number and distribution of satellites depends on the properties of dark matter and the history of galaxy assembly, making satellite counts valuable constraints on cosmological models. The relationship between Andromeda and the Milky Way extends beyond simple proximity. The two galaxies are approaching each other at approximately 110 kilometers per second. This may sound fast by terrestrial standards, but given the enormous distance separating them, the collision remains billions of years in the future. Current best estimates place the first close passage in approximately 4.5 billion years, though uncertainties in the galaxy's exact positions and velocities mean this figure could vary by hundreds of millions of years either way. Still, the collision is inevitable, unless some unforeseen perturbation alters the galaxy's trajectories. When galaxies collide, stars rarely impact each other directly. The distances between stars within a galaxy are so vast compared to the stars themselves that the probability of collision is vanishingly small. If you scattered 200 billion grains of sand across the area of North America, the grains would be farther apart relative to their size than stars in a galaxy. When galaxies interpenetrate, the stars simply pass through the spaces between each other, like two clouds of gnats flying through one another. The galaxies themselves, however, do not emerge unscathed. Gravitational forces during a galactic collision are immense and disruptive. As the two galaxies approach, their mutual gravitational attraction accelerates them toward each other. The leading edges begin to distort, stretching toward the approaching galaxy like taffy. Tidal forces, the difference in gravitational pull between the near and far sides of each galaxy, become significant. These forces tear long streamers of stars and gas from the galaxies, flinging them into space to form vast tidal tails that can extend for hundreds of thousands of light years. The first close passage scrambles the orderly structure of both galaxies, transforming their neat spiral patterns into chaotic, disturbed systems. But the galaxies do not simply pass through each other once and continue on their separate paths. Gravity slows their separation, eventually halting it altogether and pulling them back together for a second encounter. The second passage causes even more disruption, further scrambling the stellar orbits and triggering massive bursts of star formation as gas clouds collide and compress. The galaxies may pass through each other several times, each encounter extracting energy from their relative motion and depositing it into the random velocities of stars. Eventually, the galaxies lose enough orbital energy that they can no longer separate. They spiral together and merge, their hundreds of billions of stars mixing into a single, larger system. Computer simulations of the Andromeda-Milky Way collision show this process in elegant detail. Astronomers input the current properties of both galaxies, their masses and positions and velocities, then let physics run forward in time. The simulations show the galaxies approaching, interpenetrating, separating, and falling back together. They show tidal tails forming, arcing away from the collision site, like sparks from a grinder. They show the spiral structures dissolving, the orderly disks transformed into chaotic elliptical systems. The entire process unfolds over several billion years, a stately cosmic dance that will reshape our corner of the universe. The final product of this merger will be a giant elliptical galaxy, its stars occupying a roughly spherical volume, without the flattened disk structure characteristic of spirals. Astronomers have playfully dubbed this future galaxy Milkomeda, or milked Andromeda, blending the names of its two progenitors. It will be substantially more massive than either the Milky Way or Andromeda individually. The supermassive black holes at the centers of both galaxies will spiral together and merge, releasing tremendous amounts of energy in the form of gravitational waves. The resulting black hole will be even more massive than the sum of its parts, the merger having converted some mass into pure energy, according to Einstein's famous equation. What does this mean for our Sun and its retinue of planets? The solar system will survive the collision intact. The distances between stars are simply too vast for direct encounters. However, our position within the merged galaxy will likely change dramatically. The gravitational chaos of the merger will scatter stars throughout the new galaxy. Some will be ejected entirely, flung into intergalactic space to wander alone. Others will find themselves in the dense central regions, surrounded by stars far closer than any in our current neighborhood. Our Sun will probably end up somewhere in between, perhaps relocated to the outer suburbs of Milkomeda, orbiting at a greater distance from the center than we do now. The night sky for any hypothetical observers on Earth will be transformed. The familiar constellations long since dispersed, replaced by new patterns of stars mixed from two galaxies. Of course, by the time the merger occurs, Earth itself may no longer be habitable. The Sun is slowly brightening as it ages, and in approximately 1 to 2 billion years, this increasing luminosity will raise Earth's temperature enough to boil the oceans. Life as we know it cannot survive such conditions. The galactic collision itself poses no direct threat to life on Earth. The hazards are diffuse and long-term, not the sort of thing that would produce dramatic catastrophes over human timescales. Any civilization advanced enough to witness the merger will have far more immediate concerns from stellar evolution than from galactic dynamics. The stars themselves in Andromeda come in a remarkable variety of types, each with its own characteristics and evolutionary path. The most massive stars, dozens or even hundreds of times the mass of our Sun, burn with incredible brilliance. They shine with the luminosity of millions of suns, their surfaces blistering hot, colored deep blue or violet. These stars exhaust their nuclear fuel in mere millions of years, a cosmic eye bleak. When their fuel runs out, they explode as supernovae, briefly outshining the entire galaxy and seeding the surrounding space with heavy elements forged in their cores and in the explosion itself. These elements, everything heavier than helium, are the building blocks of planets and life. Every carbon atom in your body, every oxygen molecule you breathe, was created in the core of a massive star and distributed through space by a supernova. At the opposite extreme lie red dwarf stars, tiny compared to the Sun, perhaps 1/10 its mass or less. These stars burn their fuel so parsimoniously that they can shine for trillions of years, far longer than the current age of the universe. They glow with a dull red light, cool by stellar standards, producing most of their energy in infrared wavelengths, invisible to human eyes. Despite their small size and faint output, red dwarfs represent the most common type of star in both Andromeda and the Milky Way. They outnumber all of the stellar types combined, comprising perhaps 75% of all stars. Yet because they are so faint, they contribute relatively little to the galaxy's total light. The brilliant blue giants, though rare, dominate the galaxy's appearance. Between these extremes lie stars like our Sun, medium-sized yellow dwarfs that will shine steadily for approximately 10 billion years. The Sun is currently about halfway through its main sequence lifetime, fusing hydrogen into helium in its core and maintaining a stable equilibrium between gravity trying to compress it and pressure from fusion trying to expand it. When the hydrogen runs out, the sun will swell into a red giant, its outer layers expanding to engulf the inner planets. Eventually, it will shed these outer layers as a planetary nebula, leaving behind a dense core called a white dwarf that will cool slowly over billions of years. This is the fate of medium-mass stars throughout Andromeda and the universe. The standard life cycle repeated trillions upon trillions of times. Andromeda also contains numerous globular clusters, dense, spherical collections of ancient stars. Each cluster may contain hundreds of thousands or even millions of stars, packed into a volume only a few dozen light-years across. Within these clusters, stars orbit so closely that occasional near encounters occur, sometimes resulting in exotic stellar interactions. Binary star systems exchange partners. Single stars capture companions. Collisions, while rare even in these dense environments, do occasionally occur, producing exotic objects like blue stragglers, stars that appear younger than they should given the cluster's age. Globular clusters orbit in the galaxy's halo, plunging through the disk and soaring high above and below it. They serve as fossils from the early universe. Their stars all formed at approximately the same time from the same original material. By studying globular clusters, astronomers learn about the conditions that prevailed when galaxies were young. The rate at which new stars form in Andromeda provides important information about the galaxy's current state and future evolution. Star formation requires cold, dense gas, primarily hydrogen in molecular form. Andromeda contains substantial reservoirs of such gas, particularly in its spiral arms. Current estimates place the star formation rate at approximately 1 solar mass per year, meaning that each year, the equivalent of 1 sun's worth of gas condenses into new stars. This may seem like a lot, but compared to the galaxy's total stellar mass of hundreds of billions of solar masses, it represents a very modest rate. Andromeda will not exhaust its gas supply for billions of years at this pace. The Milky Way forms stars at a similar rate, despite being less massive. This suggests that star formation efficiency varies between galaxies, depending on factors like the distribution of gas, the strength of magnetic fields, turbulence in the interstellar medium, and feedback from existing stars. Massive stars inject energy into their surroundings through stellar winds and supernovae, heating and dispersing gas clouds that might otherwise collapse to form new stars. This feedback regulates star formation, preventing galaxies from converting all their gas into stars too quickly. Evidence exists for past episodes of more vigorous star formation in Andromeda's history. Certain stellar populations show signs of forming in bursts rather than at a steady rate. These bursts likely resulted from external perturbations, such as close encounters with satellite galaxies or the accretion of gas-rich dwarf galaxies. When such events occur, they compress gas and trigger enhanced star formation for a period of tens or hundreds of millions of years. Eventually, the starburst subsides as the available gas is exhausted or dispersed, and star formation returns to a lower baseline rate. The Andromeda-Milky Way collision will certainly trigger massive starbursts in both galaxies as their gas reservoirs collide and compress. The composition of Andromeda's stars varies with age and location. The oldest stars, formed over 10 billion years ago, contain relatively few elements heavier than helium. This is because the early universe produced only hydrogen and helium in the Big Bang, along with traces of lithium and beryllium. All heavier elements were created later, inside stars, through nuclear fusion. The first generation of stars contained essentially no heavy elements. When they exploded as supernovae, they enriched the surrounding gas with newly created elements. The next generation of stars incorporated these elements, and so on through successive generations. This means that younger stars generally contain higher concentrations of heavy elements than older stars, a trend observable in Andromeda's stellar populations. Astronomers call heavy elements metals, a usage that differs from the everyday meaning of the word. In astronomy, metals are any elements heavier than helium, including carbon, nitrogen, oxygen, and all the rest. The metallicity of a star refers to the fraction of its mass composed of these elements. High metallicity stars are young or formed from gas that has been enriched by many previous generations of stars. Low metallicity stars are old, formed when the universe was young and few stellar generations had occurred. By measuring metallicities throughout Andromeda, astronomers can map the history of element creation and star formation across the galaxy. The dark matter halo surrounding Andromeda represents one of astronomy's most profound mysteries. All the stars and gas we can observe, all the ordinary matter composed of protons and neutrons and electrons, accounts for only a small fraction of the galaxy's total mass. The rest, perhaps 80 to 90%, consists of dark matter, a substance that interacts with ordinary matter only through gravity. It does not emit light. It does not absorb light. It does not interact electromagnetically at all, as far as we can tell. We know it exists only because of its gravitational effects on visible matter. The evidence for dark matter in Andromeda comes primarily from studying how fast stars orbit the galaxy at various distances from the center. Newton's laws of motion and gravity predict that orbital velocity should decrease with distance from the center if most of the mass is concentrated in the visible galaxy. This is how planets orbit the Sun. Mercury moves faster than Earth, which moves faster than Jupiter. But when astronomers measure stellar velocities in Andromeda's outer regions, they find that the stars are moving faster than expected, much faster. The only explanation is that additional mass exists beyond the visible extent of the galaxy, mass that we cannot see, but that exerts gravitational influence on the stars. This invisible mass forms an extended halo surrounding the galaxy, reaching far beyond the visible edge of the disk. Current estimates suggest the dark matter halo may extend twice as far as the visible galaxy or more, perhaps to distances of 400,000 light-years or beyond. The total mass of dark matter in and around Andromeda likely exceeds 1 trillion solar masses, an order of magnitude more than the visible matter. This dark matter provides the gravitational potential well in which the visible galaxy sits, the invisible scaffold upon which the structure we observe was built. The nature of dark matter remains unknown despite decades of intensive searching. It is not ordinary matter in some dark form, like planets or dead stars or black holes. There is simply not enough of these objects to account for the observed gravitational effects. Instead, dark matter likely consists of some exotic particle predicted by extensions to the standard model of particle physics, but not yet detected directly. Many candidates have been proposed: weakly interacting massive particles, or WIMPs, axions, sterile neutrinos, and others. Experiments buried deep underground seek to detect these particles as they pass through the Earth. So far, no confirmed detection has occurred. The mystery deepens. The dark matter halo shapes the galaxy's evolution in fundamental ways. It governs how fast the galaxy rotates. It provides the gravitational binding that holds the galaxy together and prevents it from flying apart. Without dark matter, galaxies as we observe them could not exist. The visible matter alone lacks sufficient mass to create the gravitational fields necessary to explain galactic structure and dynamics. In a very real sense, galaxies are dark matter structures with visible matter embedded within them, glowing tracers that reveal the presence of invisible architecture. Observing Andromeda across the electromagnetic spectrum reveals different aspects of its nature, each wavelength range offering unique insights. In visible light, the wavelengths our eyes can see, we observe the overall structure and distribution of stars. We can distinguish the bright central bulge from the fainter disk, trace the spiral arms, and identify individual star clusters and associations. Photography in visible light has produced stunning images that grace textbooks and inspire wonder. But visible light represents only a narrow slice of the electromagnetic spectrum. Other wavelengths tell different stories. Infrared observations, made with telescopes sensitive to wavelengths slightly longer than visible red light, penetrate dust clouds that obscure visible light. Much of Andromeda's disk contains dust, fine particles of carbon and silicates that absorb and scatter visible light. This dust makes some regions opaque in visible wavelengths, hiding the stars behind them. Infrared light passes through dust more easily, allowing astronomers to see into these obscured regions. Infrared observations also reveal cool objects that emit most of their radiation at these wavelengths, including red giant stars, dusty regions around young stars, and the diffuse infrared glow from dust grains heated by starlight. Ultraviolet observations, made from space, since Earth's atmosphere absorbs these wavelengths, highlight hot young stars. Massive stars with surface temperatures of tens of thousands of degrees emit most of their light in the ultraviolet. These stars are short-lived, so their presence indicates regions of recent star formation. Ultraviolet images of Andromeda show the spiral arms lit up with brilliant hotspots where star formation is currently active. The ultraviolet also reveals the diffuse glow of very hot gas, heated by stellar winds and supernova explosions, tracing regions of intense stellar activity. X-ray observations require space-based telescopes and reveal the highest energy phenomena in the galaxy. Andromeda emits X-rays from several types of sources. The supermassive black hole at the center produces X-rays as matter falls into it, though Andromeda's black hole is relatively quiet compared to the active galactic nuclei in some other galaxies. X-ray binary stars, systems where a normal star orbits a neutron star or stellar mass black hole, emit intense X-rays as matter from the normal star falls onto the compact object. Supernova remnants glow in X-rays, their expanding shells of debris heated to millions of degrees by the explosion's shockwave. Each X-ray source tells a story of extreme physics, matter compressed to enormous densities or heated to temperatures found nowhere on Earth. Radio observations trace cold gas and map magnetic fields. Hydrogen gas, the most abundant element in the universe, emits radio waves at a specific wavelength, 21 centimeters, when its electron flips its spin relative to the proton. This emission allows astronomers to map the distribution of neutral hydrogen throughout the galaxy, seeing where gas reservoirs exist that might collapse to form future generations of stars. Radio observations also detect synchrotron radiation from relativistic electrons spiraling in magnetic fields, revealing the strength and structure of magnetism throughout the galaxy. These magnetic fields influence how gas moves and how stars form, yet they remain difficult to study without radio observations. The Hubble Space Telescope has observed Andromeda in unprecedented detail, its sharp vision unblurred by Earth's atmosphere. Hubble has resolved individual stars in Andromeda's disk, something ground-based telescopes struggle to accomplish at that distance. It has studied star clusters, mapping their properties and ages. It has examined the regions surrounding massive stars, where stellar winds and radiation sculpt the surrounding gas into complex shapes. Hubble's observations have revealed dust lanes threading through the galaxy's spiral arms, sites where dense clouds block light from background stars. These observations help astronomers understand star formation, stellar evolution, and the interstellar medium in a nearby galaxy where we can study these processes in detail, impossible in our own Milky Way. Ground-based telescopes have not been rendered obsolete by space observatories. Modern ground-based instruments equipped with adaptive optics can compensate for atmospheric turbulence in real time, producing images nearly as sharp as those from space. Large ground-based telescopes also have advantages in collecting area, allowing them to gather more light and observe fainter objects. Some of the most detailed spectroscopy of Andromeda comes from ground-based instruments, which disperse the galaxy's light into spectra and analyze the detailed patterns of absorption and emission lines. This spectroscopy reveals chemical compositions, velocities, temperatures, and densities throughout the galaxy. Amateur astronomers have made significant contributions to Andromeda studies as well. Equipped with modern CCD cameras and computerized mounts, dedicated amateurs can produce images rivaling professional work from decades past. They have discovered novae in Andromeda, sudden brightenings caused by thermonuclear explosions on the surfaces of white dwarf stars. They monitor variable stars, tracking changes in brightness that reveal information about stellar physics. They have created detailed maps of the galaxy's structure from painstaking series of observations. The democratization of astronomical technology has opened galactic astronomy to anyone with sufficient dedication. Each wavelength, each type of observation, contributes pieces to the puzzle of understanding Andromeda. Like the parable of blind men examining an elephant, each approach reveals different aspects of the truth. Visible light shows the stars. Infrared penetrates dust. Ultraviolet highlights star formation. X-rays reveal extreme physics. Radio traces gas and magnetism. Only by combining information across all wavelengths can we construct a complete picture of this complex system. Given the vast number of stars in Andromeda, the question of planetary systems naturally arises. If stars in our galaxy commonly host planets, and current observations suggest they do, then Andromeda must contain hundreds of billions of planetary systems. The same physical processes that form planets around stars in the Milky Way operate in Andromeda. Stars form from collapsing gas clouds, and the conservation of angular momentum causes the remaining material to settle into rotating disks around the newborn stars. Within these protoplanetary disks, dust grains collide and stick together, gradually growing into larger bodies. Eventually, some of these bodies reach sufficient size that their gravity dominates, allowing them to clear their orbital zones and become planets. Current technology cannot detect individual planets in Andromeda. The galaxy is simply too distant. The most successful planet-finding technique, the transit method, requires observing a star's brightness dip slightly when a planet passes in front of it. This works well for nearby stars, where we can measure brightness changes of a fraction of a percent. But in Andromeda, even individual stars are difficult to resolve, let alone monitor with sufficient precision to detect planetary transits. The alternative method, measuring the gravitational wobble a planet induces in its parent star, also fails at such distances. The wobbles are too small, the stars too faint, the distances too great. Yet we can estimate the number of planets in Andromeda using statistical reasoning. Studies of nearby stars in the Milky Way show that planets are common. Most stars appear to host at least one planet, and many have multiple worlds. If this holds true for Andromeda, and there is no reason to think otherwise, then the galaxy contains at least as many planets as stars, perhaps 1 trillion worlds circling their parent suns. Many of these will be gas giants like Jupiter, massive worlds unsuitable for life as we know it. Others will be rocky worlds like Earth or Mars, their surfaces solid, their masses manageable for terrestrial life. Some fraction of these rocky worlds will orbit in the habitable zones of their stars, the range of distances where temperatures allow liquid water to exist on the surface. Water is essential for life as we understand it, serving as a solvent for biochemistry and a medium for molecular interactions. A planet in the habitable zone has a chance, not a guarantee, of developing life. Many other factors matter: the presence of an atmosphere, the composition of that atmosphere, the planet's magnetic field, the stability of its orbit, the intensity of its star's radiation. Still, if even a small percentage of habitable zone planets develop life, Andromeda could be teeming with living worlds. The possibility of intelligent life, of civilizations like our own or more advanced, remains pure speculation. We have no evidence either way. The Drake equation attempts to estimate the number of communicative civilizations in a galaxy by multiplying together factors like the star formation rate, the fraction of stars with planets, the fraction of those planets suitable for life, and so on. Each factor contains enormous uncertainty, and multiplying uncertain factors compounds the uncertainty. The result could be that advanced civilizations are common, with thousands in Andromeda alone, or that they are vanishingly rare, with humanity representing the only technological species in our local group of galaxies. We simply do not know. If civilizations exist in Andromeda and attempt to communicate using radio signals, their messages would take 2.5 million years to reach us, traveling at the speed of light. Any signal we detected today would show their civilization as it existed when our ancestors were Australopithecus afarensis, small-brained bipedal apes, just beginning to make the simplest stone tools. If those distant beings aimed a telescope at Earth today, they would see it as it was 2.5 million years ago, long before cities, before agriculture, before art or writing, or any of the trappings of civilization. They would see a planet populated by animals, with no obvious signs of intelligence. The vast gulfs of space impose an isolation so profound that even if the universe teems with civilizations, communication between them may be effectively impossible. This cosmic isolation is both humbling and somewhat reassuring. Humbling because it emphasizes how small and insignificant we are in the context of the vast universe. Reassuring because it means that if hostile civilizations exist, they are trapped by the same limitations of distance and time that constrain us. Science fiction often depicts easy travel between stars and even galaxies, fleets of spacecraft crossing the cosmos. Reality is less accommodating. The energy required to accelerate even a small spacecraft to an appreciable fraction of light speed is enormous, and the time required to cross intergalactic distances is measured in millions of years, even at such speeds. Andromeda serves as a mirror in which we can see aspects of our own galaxy invisible from within. Living inside the Milky Way, we cannot step back and view its overall structure. We see it edge on from within the disk, the majority of its stars hidden behind dust and distance. Andromeda, viewed from outside and tilted at a convenient angle to our line of sight, reveals its spiral structure clearly. By studying Andromeda's morphology, stellar populations, and dynamics, we learn about the general properties of spiral galaxies, properties that likely apply to the Milky Way as well. The two galaxies are similar in many ways, both large spirals with comparable masses and structures. Understanding Andromeda helps us understand our own cosmic home. Yet Andromeda is also humbling in another sense. It is one galaxy among billions, perhaps trillions, in the observable universe. If we could somehow step back, farther, view not just our local group, but the entire cosmic web of galaxies stretching across billions of light years, Andromeda would fade to insignificance, one more mote in an incomprehensible vastness. From the right perspective, even galaxies are small. The universe is larger than we can truly comprehend, its scales exceeding the capacity of human intuition. We can calculate distances and times, write them down as numbers, but we cannot really feel what they mean. 1 million years is already beyond our grasp. 1 billion is impossible. Yet these are the timescales on which galaxies evolve, the intervals between major events in their histories. From ancient Persian observations as a mysterious cloud to modern studies revealing its nature as a vast galaxy, our knowledge of Andromeda has grown exponentially. Yet fundamental mysteries remain. The nature of dark matter, which comprises most of the galaxy's mass, eludes us. The details of galaxy formation and evolution continue to puzzle astronomers. The question of whether life exists on any of Andromeda's trillion possible worlds remains entirely unanswered. We have learned much, but much more remains unknown. This is perhaps the most exciting aspect of astronomy, the certainty that future generations will discover things we cannot yet imagine, answer questions we have not yet thought to ask. The collision between Andromeda and the Milky Way will reshape our cosmic neighborhood over the next several billion years. The merger will be one of the last major events in the history of our local group. After Milky forms, its future will be one of gradual evolution, star formation declining as gas is exhausted or expelled, stellar populations aging, the galaxy slowly fading as massive stars exhaust their fuel and no new ones form to replace them. On even longer timescales, far in the future, proton decay or black hole evaporation may dismantle the galaxy entirely. But that lies trillions of years ahead, timescales so vast that the current age of the universe represents a mere opening instant. For now, Andromeda hangs in our sky, a reminder of the vastness of space and the grandeur of cosmic architecture. It reminds us that we live not on a planet in a solar system, in a galaxy, but on a planet in a solar system, in a galaxy, that is part of a local group, that is part of a supercluster, that is part of the observable universe. Each level of structure encompasses the last. Scales nested within scales. Complexity emerging from simple physical laws, operating over cosmic time. Andromeda represents both what we know and what we have yet to learn, a target for our telescopes and our curiosity, a subject we will study for as long as civilization persists. The light leaving Andromeda tonight will arrive at Earth in 2.5 million years, carrying information about a galaxy that exists in our present, but will be observed by whatever beings inherit the Earth in the distant future. They will see Andromeda not as we see it now, but as it will be then, changed by time. Drawing nearer, perhaps, already beginning the initial stages of collision with the Milky Way. They will have knowledge we lack, technologies we cannot imagine, perspectives broadened by millennia of discovery. They will still be looking at the same object, Andromeda, our nearest large galactic neighbor, a fellow traveler through the cosmos, approaching across the void for a meeting already written in the equations of gravity, inevitable and profound.